Hello all, in this video we will be solving one question regarding the VLSI which came into GATE 2020. Now let us read the question, then we will be solving this question. Okay, so the question which is saying that you have given some circuit and you have given also the propagation delay, setup time and the hold time for the flip-flop. Now they are asking what is the maximum clock frequency at which the given circuit can operate reliably. So the maximum frequency at which you can run this circuit, we need to find it. Before we solve this kind of question, we need to have the familiarity with the setup time, hold time and the propagation delay for the flip-flop. So let us understand these three definitions for the delay. Let's say you have some D flip-flop. Okay, so this is the data which is the input to the D flip-flop, and let us say this is the clock. Now assume this flip-flop is positive edge triggered flip-flop. This is the output for the flip-flop. In the ideal case, what happens? Let's say you have some data. Okay, so this is the data D, and let us say you have some clock. Okay, let us say this is the clock. Okay, now in the ideal case, what happens? The moment you sample the data, the output will come. So the output will be coming immediately after you sample the data. Okay, so at this age only the output Q will be coming. So in the ideal case, we assume that the propagation delay for the flip-flop is 0. But in the reality, what happens? This output Q takes some times. Okay, so let us say this is the output in the practical case. So the moment you sample the data, after some time output will be coming. So this is the delay which we call the propagation delay for the flip-flop. Okay, so from the clock age to the output Q. Okay, so this is the delay, TPD. Sometimes we also call this delay as TCQ. That means clock to Q delay, because this is the delay from the clock age to the real output Q. Yes, so you can see this is the clock to Q delay. So this is the one time delay for the flip-flop. Now let us talk about the setup time and the hold time for the flip-flop. Okay, now once you know these three definitions, propagation delay, setup time and the hold time for the flip-flop, this question you can solve within a minute. I will be solving this question within a minute. You can see that later. Okay, so let us first understand what is the setup time. So sometimes we also denote this as TSU. Okay, setup time. Now assume we have one D flip-flop. So this is the data again, which is the input for the D flip-flop, and this is the clock. Assume this flip-flop is positive edge triggered flip-flop. Okay, and this is the output Q. Now so this is some kind of constraint for the flip-flop. Okay, so setup time and the hold time gives some constraint over the timings for the flip-flop. Okay, so there is some rule by which we should be going. Okay, so this is not that you can apply this data at any time and you can remove the data at any time. No, we should follow some rules, and they give us the setup time and the hold time constraint. Okay, sometimes we call the hold time constraint and the setup time constraint because it limits us in times in terms of the timing capability, in terms of the like when we can apply the data, when we can apply the clock and all these things. Okay, so let us understand this in detail. Now let us say my clock is coming. Okay, so this is the, let's say, clock. Okay, now the setup constraint, what is the constraint? It says, let's say at time T this clock is coming. Now at least T setup time before my data should be arrive. Okay, and be there and do not change. Okay, so data at least t setup times before should come and be stabilized there. Okay, so from the t time period, at least t setup time before, my data should be like maybe changing here, but at least here my data should be stabilized. Okay, so what the setup time says, this is the time before the t clock age. Okay, so at least t setup time before my data should come and be stabilized there. Okay, so after this so this is the t, let's say this is the t, so t minus t setup time before, so this is the instantaneous time. Okay, okay, so let's say this is the t time instant, and so t minus t setup time instant before my data should be stabilized. Okay, after that this data should not change. Okay, so you cannot change this data here. Okay, you can change this data here, but t setup time before the data must be stabilized. Okay, so this is the constraint. Okay, now data can stabilize here also, we don't have any problem, but at least t setup time before this clock age my data should be stabilized. So this is the constraint on the t setup time. Now similarly we have the hold time constraint also. Now what is the hold time constraint? So this hold time constraint says that after the clock age you cannot remove this data immediately. So okay, you sample the data at this clock age, but don't remove or don't change this data immediately after the clock age. You just keep this data for some time also. Okay, so before this clock age, let's say t setup time. Okay, so this is the minimum time period before which the data should be stabilized, and after the clock age, at least for t hold time we should be stabilize the data. Okay, so before the clock age we should be having some timing, which is the t setup time. So after this time instant the data should not change. Okay, and similarly after the clock age, for whole time duration we should be having the stabilized data. So let's say this is the clock age. Okay, so before this clock age and after this clock age we have some timing constraint. Okay, so data might change here, but it should be stabilized here to 1 or to 0. Okay, but at least t setup time before it should stabilize. Similarly after t hold time data might change, we don't have any problem, but at least for t hold time more after the clock age we should have the stabilized data. Then only, so once you satisfy these setup time and the hold time constraint, then only you can reliably, okay, then only you can reliably sample this data. Okay, maybe you are not following these constraint, maybe you will just change the data, let's say in this time period, and you just apply the clock age, you will be able to sample the data, but you may not get the correct output. Okay, so the output queue after sampling which you will get may not be the correct, and there are various issues like meta stability and some hazard issue are there. So if you violate these kind of constraint, so the output which you are getting, which is very disturbed output. Okay, so this is not guaranteed output that this is the correct. Okay, so now you know this, what is the setup time, what is the hold time, and what is the propagation delay. We can solve this question. Okay, so let us solve this question. Now we will be solving this question within a minute. Okay, so for sake of understanding we may take some time, but believe me, if you know this kind of definition you will be able to solve this kind of question within a minute. Okay, so let us solve this now. So we need to find the maximum frequency. Maximum frequency means minimum time period. Okay, so we need to find minimum time period for the clock, okay, at which we can operate this circuit. Okay, so what is the minimum time period which I should give? That means once you change this clock, now after what time I can change this or I can able to apply this clock age, second clock age. Okay, so this is what my time period is. So this is the minimum time period I need to find. So let us first find okay, let us just analyze this circuit first. Okay, so assume you just gave some data D here, Okay, so after TPD, so after 3 second of delay, after 3 nanosecond of delay, this data should be arriving here. Yes, now these are the propagation delay for these gates. Okay, so 2 plus 2 4, so after 4 nanosecond, so 3 plus 4 total will be 7 nanosecond. This data from here to here, here it will be coming. Okay, so we came up with this data here. Okay, now this data will go here and will come arrive at this point. Okay, so after like 7 nanosecond, after 7 nanosecond we came up this at this point. Okay, now what I need to do, okay, sorry, okay, so at the 7, after 7 nanosecond we come up at this point. Okay, now our requirement is like we want to sample this data from this flip-flop, so we have to follow the setup time and the hold time constraint. So forget about the hold time constraint for now because it is not useful. So before the second clock edge, so at the first clock edge, let's say you sample at this flip-flop. Okay, and the second clock edge you want to, so this is the first clock edge, this is the first clock edge, and this is the second clock edge. Okay, so at the first clock edge you sample the data, and after 7 nanosecond, after 7 nanosecond you came up at this point. Okay, now before you can sample this arrived data at the second clock edge, we need to have at least 4 nanosecond margin. Yes, so before we can sample this data at this clock edge, so at least 4 nanosecond this data should be coming and be stabilized there. Okay, so 4 nanosecond margin plus 7 nanosecond which is it is taking. Yes, so total of 11 nanosecond we need for this clock. You got the point? Yes, so 7 nanosecond which is for this propagation delay. Okay, and 4 nanosecond before, 4 nanosecond before this data must be arriving, so that we can sample this data at least at the second clock edge. Okay, so let me make a diagram for you just for understanding what I'm saying. We have 2D flip-flop. Okay, so from first so the same clock is given to both of the flip-flop first of all. Okay, so this is the same clock which is given to this flip-flop and D flip-flop also. Now at the first clock edge data is sampled from the this first flip-flop. Okay, let's say this is D1, this is a D2. Okay, this is the connected. Now we want to find at least what time later we can have the second clock edge. That means what is the minimum time period we can have. Okay, so let's say at this first clock edge you sample the data from this first flip-flop. Now it will take some T propagation delay. Okay, and there is some combinational circuit. Let us say this is the T combinational. Okay, and we looked at the setup time constraint that at least before you sample the data, at least T setup time before this data which is coming from here to here should be arriving. Yes, so this propagation delay plus this propagation delay and the setup time margin. Okay, so TPD for the flip-flop plus T combinational delay plus T setup time. Okay, this much time at least we need before you apply the second clock edge. Yes, so then only you will be able to sample this arrived data. Okay, so this flip-flop setup time constraint says, okay, I can sample this data, but at least I need the stabilized data T setup time before. This is the setup time constraint. So we said, okay, so this much of time we are taking and T setup time is the margin. Okay, now you can sample the data. Okay, now so this is the minimum time period. Okay, now this clock edge can come after like this time period also. Okay, but we need the minimum time period, so this is the minimum time period which we need to have for the clock. Okay, so similarly this is what we are trying to do. Let me just erase this. Okay, let me just erase this. Okay, so what we are trying to do, so this is the 3 nanosecond. Okay, and this is the 4 nanosecond. Okay, so this is the 7 nanosecond. Okay, and at least this 4 nanosecond before you apply the second clock edge for this D flip flop, at least 4 nanosecond before this data should be coming. So this 3 plus 4 plus this 4 setup time. Okay, so this is the minimum time period if you go by this path only. Okay, so 4 plus 4 plus 3, which is the 11 nanosecond. Okay, now you just assume the second scenario. Okay, second scenario is this. Let us say, so first scenario was you are applying the input here and you are checking with respect to arrival at this a point. Okay, now assume the second scenario. What the second scenario is saying, let me erase this. Second scenario is this: you apply the input, you apply the data at this flip flop. Okay, so it will take 8 nanosecond because propagation delay for this flip flop is 8 nanosecond. Okay, now this output will be going here and will be coming at this point. Now before you apply this second edge of the clock, okay, so we need to have at least 5 nanosecond margin. So this data should arrive at least 5 nanosecond before the second clock edge. Yes, so this 8 nanosecond plus 5 nanosecond, which is the total 13 nanosecond. Okay, so only after 13 nanosecond you can apply the second clock edge. Okay, so after first clock edge you can apply this clock edge only after 13 nanosecond later if you go by this path. Okay, so this is the 13 nanosecond. So at least we have to have this 13 nanosecond of clock period. Why? Because if we have the clock period of, let's say, 11 nanosecond, okay, then let's say if the data goes by this and this, so this will be violating the setup time for this path. Yes, so if we have the 13 nanosecond, this path will be also satisfied because we need only the 11 nanosecond, but we are giving the 13 nanosecond. It is okay. Okay, and for the 13 nanosecond, this path will not violate the setup time and the hold time constraint. Okay, so in general we need to have the 13 nanosecond minimum time period, then only we can operate this circuit reliably. Okay, so this is also they are saying in the question that we need to operate reliably. Okay, so this is what they are calling. So even if you apply the 11 nanosecond clock period, okay, 11 nanosecond period, what might happen, this circuit might work correctly, but in some cases this will not be working correctly. Why? Because this flip flop, for this flip flop, let's say the data coming from here to here, so we are not following the setup time constraint. 5 nanosecond we are not coming before this second clock edge. Okay, so only if you give the 13 nanosecond clock period, then only you will be able to follow the second constraint. Okay, so now we found that minimum time period is 13 nanosecond. Okay, now you have the minimum time period, you can say maximum clock frequency. So maximum clock frequency will be 1 by 13 nanosecond. Okay, so if you will solve this, so you will be finding 76 to 77 megahertz. Okay, so this is the output you will be getting. So you just need to find the minimum time period which we need to apply for this circuit to operate reliably. Okay, so this is what the question was asking. Now you can have multiple questions based upon that. Sometimes they will be giving some critical path, some critical circuits, so you just need to find what is the minimum time period we need to apply so that we can able to follow the constraint the setup time constraint and the hold time constraint. Okay, so the answer for this will be 76 to 77 megahertz. I just try to solve, because if you will solve 1 by 13 nanosecond, it will be around this only. Okay, so thank you. In the next videos we will be trying to solve the more question regarding this, and if you have any query you can like comment in. Okay.